Hey everybody, welcome to Math with ACE, focusing on statistics. We are continuing our chi-squared exploration. So in this question, we are asked, is gender independent of education level? So when you're trying to figure out whether this is chi-square goodness of fit, independence, or homogeneity, the fact that the problem says independent is probably a pretty clear indicator. Also, there's a two-way table. It's not just a single distribution of proportions. So that's also another indicator that we're probably doing a chi-square test of association focusing on independence. Let's continue reading though. A random sample of 395 people was surveyed and each person was asked to report the highest education level they obtained. The data resulted in the survey summarized in the table. We have female, not female, high school, bachelor's, master's, and PhD level of education. So are gender and education level dependent at a 5% level of significance? In other words, is there a relationship between the gender of an individual and the level of education they've obtained? So we're trying to figure out if there's a connection here. We are in a single population with two different groups. So this isn't a test for independence. So our null hypothesis is going to be that gender and education level is independent. The alternative that we're trying to find evidence for is that they actually have a relationship and are dependent. You can also say not independent instead of dependent. Either one works. And we're testing this at the alpha equals 0.05 level of significance. We need to check conditions. Can we generalize this information? Can we use the appropriate test statistic? Is this good data that we're using? So random. Was the data randomly selected? It does say a random sample of 395 people were surveyed. So data was randomly selected as stated. What about independence? Was our sample small in comparison to our population? We don't want to have to worry about sampling with or without replacement. 395 times 10 equals 3,950. Well, we're talking about, they don't really give us a population. They're just saying a random sample of 395 people surveyed. Where are these people? I would say it's safe to assume that from this group, there's at least 3,950, because whether we're talking about a city or somewhere else, it's a pretty safe assumption that there's that many people in that city. So it is safe to assume there are at least 3,950 people in the population. Now, what about expected counts? Expected counts mean that the large counts need to be at least 5. And the way that we calculate the large counts is we are going to take the row total times the column total and then divide that by the overall total for each female category and each not female category. So we have 8 different expected counts that we're going to be calculating. So let's say for high school and female, I'll create my own little table since I didn't copy and paste it. And I'm going to abbreviate. And then not female. So we have high school, we have bachelor's, we have master's, and we have PhD. So I'm going to take 201 times 100, which is 20,100, and divide that by 395 to get the expected counts for the first row, first column. Female bachelor's means 201 times 98, which is 19,698, and divide that by 395. That gives me 49.868. Again, we are not rounding these. We are leaving them as is. Master's in female means I'm taking 201 times 99, which is 19,899, divided by 395, gives me 50.377. And then PhD in female is 201 times 98, which is 19,698, dividing that by 395. And I get 49.868. Now I need to do the same thing for not females. Not female high school would be 194 times 100, or 19,400. Divided by 395 gives me 49.114. Not female bachelors would be 194 times 98, which is 19,012. Dividing that by 395 gives me 48.132. Masters in not female is 194 times 99, which is 19,206. Dividing by 395 is 48.623. And then 194 times 98. It's going to be the same thing as the previous not female bachelors. Dividing by 395 gives me 48.132. Now, in order to calculate the test statistic and use the chi-square distribution, I need my degrees of freedom, which is the number of rows minus 1 times the number of columns minus 1. There are 2 rows and there are 4 columns, which means I have 1 times 3, or 3. So I have 3 degrees of freedom. So if I was to calculate the test statistic by hand and run these numbers to get the test statistic and use the chi-square distribution on Stapplet, I need to know my degrees of freedom are 3. Let's go ahead and put the chi-square statistic together. And I'm going to make it off to the side a little bit so that I can use the numbers all together. So the chi-squared statistic is going to be, did not mean to make that in gold. The chi-squared statistic is going to be, let's do high school female. We observed 60 minus 50.886 squared divided by 50.886. Adding that to bachelor's female, we observe 54 minus 49.868 squared over 49.868. Plus master's female, we observe 46 minus 50.377 squared over 50.377. Adding that to a PhD female, we observe 41 minus 49.868 squared over 49.868. Moving on to not female high school, we observe 40 minus what we expect squared over the expected. Plus bachelor's not female is 44 observed minus the expected. Plus master's not female, we observe 53 squared over what we expect. Plus, lastly, 1, 2, 3, 4, 5, 6, 7, PhD not female, 57 observed minus the expected. Okay. So then we would sum all of that. You can see it in the top right-hand corner. My image might be over. If I scroll down on the right-hand side, you can see all of those values together. I'm now going to use Stapplet to help me actually calculate this test statistic and put these values in. And in Stapplet, I actually don't need to do the expected counts. They're going to do it for me, but it's good practice to know where they come from. So here we go. Stapplet is going to be, we're doing 2 categorical variables, and in order to be consistent with the way that the chart is, I'm going to have the education level here and gender on the side. I don't know that I would say that that's the explanatory versus response, but I want the table to match the orientation that y'all have. High school, bachelor's, master's, and PhD. And then we have female, expected counts, no, I'm sorry, observed counts, not female, 40, 44, 53, 57. And then I begin my analysis, scroll down, and you'll see the percentage of each in the overall group. And then we perform that chi-square test for independence. And if you look at the top of the two charts that you see, you'll see the expected counts match the counts that we had. This is giving us a chi-squared value of 8.006 and a p-value of 0.0459 with the degrees of freedom of 3 like we calculated. So now we have enough information to make our conclusion. And what we can say is, since our p-value of 0.0459 is less or not our 5% level of significance. What do you think? It is less than our alpha equals 0.05 level of significance. What do? This means that we would only get this data about 4.59% of the time if our null really was true, which is pretty small. So it's likely that our null is not true, and we have evidence to support our claim that they are dependent. So we are going to reject the null because there is sufficient evidence to support the claim that, going up to the null, are the alternatives that gender and education level are dependent. Right. So because gender and education level are dependent, that means that the chi-squared statistic was large enough to have a difference at that degrees of freedom based on the curve. Waiting for my screen to catch up here. But what you're not seeing in the words is that there is sufficient evidence to support the claim that gender and education level are dependent. Hopefully this was helpful. It concludes our chi-squared exploration. We're going to move into analysis of variance next. Thanks for watching.